then. So welcome everyone to this Thursday's virtual time series seminar. I'm happy to introduce you Matteo Barigozzi from the University of Bologna, and as a guest, as a speaker, and as a guest panelist, Esther Ruiz from Carlos III. So Matteo is going to speak about factor-adjusted network estimation and forecasting for high-dimensional time series. So thank you very much for accepting our invitation, and the floor is yours.
Okay, thank you very much, Alessandra, for the introduction. Thank you for inviting me. Actually, I don't know, from the day Michele and Majid started this thing long time ago, that they tried to be included in the mailing list, but I was never able. I started thinking you didn't like me. Okay, no, besides the joke. So this is a joint work with Haron Cho and Dom Owens at the University of Bristol. Haron is a co-author of mine since a long time. Actually, she pushed a lot to do this paper. I was really skeptical, but in the end, I think we did manage to do something nice. So some of you probably already seen this presentation, and I hope it will be not too boring to hear it again. Okay, sorry, there is an advice here. Okay, good. So let me give you a setup. Okay, so the setup is a panel of time series, P time series observed over n periods, and think of modeling them as a VAR of like D. Okay, with some innovation in T with covariance matrix G. Okay, so this is a classical tool. We can be used a lot in time series. It's still used a lot. Interesting. Last summer I was at the JSM, and I've seen that in astrostatistics, apparently VAR and VECM are still very good to do analysis of finding new planets. Okay, so not the only tool, but it's one of the main tools people were using. So nothing very fancy, but still very, very important. And then there are recent work, and have been many works showing that, on the other hand, by looking at the parameters of these models, so the coefficient A of L, and often the inverse of the covariance matrix G, you can give an interpretation in terms of network. In fact, the interpretation is in terms of partial conditional correlations, which are usually mapped into networks. This is the idea of graphical models that goes back to a long time ago. There are works by Dalaus on this, by Michael Eichler, and then there is a paper by Christian and myself, for example, where we took this approach. We estimated the VAR the way you see written above, and we define a series of networks. Okay, so A of L would be the Granger network, the inverse of G, the partial correlation network or contemporaneous network. And then when you put everything together, the thing you see there is nothing else but the inverse of the spectral density matrix of X at frequency 0. That's a longer run partial correlation network. Okay, so now the problem is the curse of dimensionality, of course. How do we estimate this thing here when we have P that is very large? That's a big problem. Obviously, classical methods will not work, and one can think of using sparse models. But on the other hand, there has been a lot of use of denseness, so factor analysis, for example, to model high-dimensional vectors of time series. So now the question is which one of the two to use. And on this, our starting point was to notice that the sparse estimation, so if you want to estimate this VAR using something like lasso, so assuming some sparsity on A of L, then you must assume that the largest spectral eigenvalue of X is bounded. Okay, this is shown in Basel-Michailidis. Unfortunately, they call this condition stability, but that has nothing to do with stability of a time series. Okay, this is another kind of stability that they have in mind. Stability meaning that the largest eigenvalue of the spectral density matrix of X is bounded for all P. Okay, and if the dimensions are high, then you must assume a high level of sparsity for that condition to hold. Okay. However, we know that many economic data do not show this feature. In fact, they show denser structures. Okay, there is the recent paper by Domenico Lenz and Primiceri on econometrica showing that, but that is an idea that goes back more years, and I particularly like this, the Molja non-hierarchical journal of econometrics, which is a very nice paper using the classical macro data set and showing how lasso forecasts are all over the place with respect to forecasts done with ridge or with factor models, where ridge is a dense model, or is a dense way to model this kind of data, okay? And on the other hand, there are theoretical results that tells us that if you have common factors, then you will have spiking spectral eigenvalues, in the sense that if P increases, the eigenvalues of the spectral density matrix, at least the largest one, will explode. But most importantly, the result by Forni and Lippi, and then Forni, Hallan, Lippi, Reiklin, and then a recent paper, more recent paper by Hallan and Lippi, show that it's also true the vice versa. If there are spiking eigenvalues, then there are common dynamic factors. This is not straightforward to prove, okay? So if you find that, and you follow that theorem, then you should include the presence of dynamic factors. Dynamic factors in the sense that they're common factors that are loaded by the series also with legs, possibly with infinite legs. Okay, and to show you that what I mean, this is an example done with the data set that we analyze in this paper. We have 46 volatility measures. And then on the horizontal axis, you see the cross-sectional dimension. So that's P growing. So what does it mean? When you see 2, we said we took randomly 2 series out of 46, and we computed the spectral density, and we look at the 2 largest eigenvalues, the blue and the red. And then we go on doing that as P increases. So when you use all of them, the largest eigenvalue is up here. The smallest eigenvalue is still very low. So obviously, we cannot claim that this is diverging to infinity, but come on. I mean, we see something happening here, okay? We see that every time a new time series comes into the game, the first eigenvalue grows, and it grows almost linearly if you look carefully, okay? Which is also very interesting. I will not touch on that, but it tends to grow linearly. At least for the largest eigenvalue, this is a behavior that you will find very often. But if this is the case, I strongly doubt that you can assume sparsity directly, okay? Because that will violate the idea that the largest eigenvalue is bounded for all P. I don't see it being bounded anyway, okay? Obviously, this is an empirical result. The theory is another thing. P going to infinity will never happen, but I've done this kind of graph for many other data sets, and this is what you find most of the time, and I'm sure that some of you have done the same, so it should not come much as a surprise. On the other hand, one can look at things from another point of view. Okay, let's assume that we take the same panel and we estimate a VR5 through ridge, because this is too large to be estimated with OLS. And then there is a way to test for Granger causality even when you estimate with ridge. Here is a reference. And then you can compute p-values for Granger causality and use Bonferroni correction. This is a rough approach, but just to give you an idea. And then what you see here is that basically there are no zero entries, okay? So this tends to be dense, okay? The redder is the dot, the more the smaller is the p-value, meaning you are strongly rejecting the null of no Granger causality, okay? So based on these observations, then probably one should not start directly estimating a sparse VAR on a large panel of this kind of time series. There might be some where you can do that, okay? So you first should control for common factors, and then maybe look for residual dependencies. This is what we do here, okay? And which kind of dependencies? Well, here we stress the fact that we deal with conditional dependencies and dynamics. So we care about estimating A of L and G, but not on the data that we observe, but on the data after we control for common factors. So this is what we're going to do, okay? An example for finance, this means that we know that in financial markets there tend to be 2 complementary features of about which people are interested: global factors, which are the systematic component of risk. This is the part which is non-diversifiable. That if you just take an average of the stock returns, you get the stock market index, which moves strongly with all of them. But there are obviously firm and specific idiosyncratic components which are important. There are studies about them. They're usually, to study them, you study the conditional dependencies, so A of L and the inverse of G. This is what we were getting with Christian, where we're controlling for observed factors on a panel of log volatilities. This is what I found with Mark on a similar data set, estimating adaptive lasso after removing a common factor. And you see that the results show that there is more sparsity, okay? The left-hand side is A of L, VAR1, so this is the coefficient matrix, and this is the inverse of the covariance matrix of the residuals of the VAR, okay? Estimated with adaptive lasso. And well, here we highlighted two sectors. This is financial and energy sector, which seem to be strongly connected within. Okay. So based on all this is our contribution. So we assume that xt is in fact the sum of two components, a common component chi t, which is driven by few common dynamic factors ut, which are white noise in this setting, okay, and they are orthonormal. And then the residual component, the idiosyncratic component, follows a VAR, parameterized in this way, which is convenient for us. And the coefficient of this filter will be sparse in a way that we specify later on. Okay, so we have a low rank component plus a sparse component. Okay, an estimation will be through dynamic principal component to control for this term, and then estimating this sparse VAR, not exactly through lasso. So I will show you that we use a different approach, which seems to be more convenient. What we prove is consistency of all the estimated quantities as NMT go to infinity. And in particular, I want to stress the fact that we have a uniform rate of consistency. So these are uniform over I and T, meaning this is a contribution to the literature of generalized dynamic factor model for which this result didn't exist. So this is really telling what can go wrong. Right? In the worst case, this is what you get. Okay, so we do not just take the result by Forn et al. We work on them and we improve on their results. So literature, there is a huge literature on sparse VAR. So until the last revision, we were stopping here, and then referee asked to us at the 4 other papers, and they keep appearing, okay, on sparse VARs. They are all interesting. They all tend to move from one to the other. Assumptions are weakened. The last one, I think, is the most general I know for the moment. But in this sense, we also contribute to that because we have a different set of assumptions from some aspects even more general than what you see written here. Then there is literature on networking time series, starting from the Laus and going on. There is the literature in generalized dynamic factor model, which I already mentioned and I will not mention again. And then the idea of factor plus sparse, well, first there is the paper that I did with Mark, but that was a purely empirical paper. And then there are 3 papers by Jianxin Fan and co-authors where they use the static approach, so just principal component plus sparse. Actually, this 2020 is estimating everything in one shot, so that's very interesting. The other 2 are 2-step estimation methods, analogous to ours. So the other 2 actually are nested into our approach, basically. And this we show in the paper that if you just assume that instead the factor model is a static one, so factors are not loading with legs, you will recover exactly the same result that they have. And Margaritella and Kramp have something similar on that, although they use a different definition of sparsity, so it's not entirely directly comparable with ours. Okay, so in fact, this is now published in 2023, and I think this one as well. So they all appear at the same time, the papers. Okay, so we will work with this approach. It's important to remember that under our assumption, which is stationarity and causality of the VAR, we actually can also write the world representation of the idiosyncratic component, which I will use in a moment. And we will be making assumption on D of L, and this will have an effect on the rest, okay? And then this I will skip. I will use it if I have time. So let me just go on. So once we have the idiosyncratic component models and the VAR, the definition of networks that we will use, so what we're going to estimate are the edge sets of these 3 networks. The Granger causality network, which is defined in this way. So as long as one of the polynomial of the matrix A of L has an entry different from 0, there is we draw a link between I and I prime. The contemporaneous one is based on the inverse of the covariance matrix of the innovations, which to make it a correlation, you have to do this transformation with this minus in front. But basically, if delta I prime is different from 0, then also this term obviously is different from 0, and you will draw an edge on this other. You will have an edge on this other set, and then combining the 2, you will have this matrix omega, and from omega you can build a partial correlation by again the same kind of rescaling and the same reasoning. We have E of L, which is the long-run partial correlation network edge set. Okay, so the final goal is double. First of all, to estimate these 3 edge sets, And second of all, to see if this approach can allow us to forecast. Then we will not care about this 3-edge set, but just directly from A, try to forecast Xi, okay? Plus a forecast of the common component, okay? In fact, if one manipulates the whole model and assumes that the common factors here are not loaded with infinite legs, but only with a finite number of legs, then it is well known that the model can be written as a static model with static factors. And then if one goes on and tries to work out what is the one step ahead a prediction for a variable x, you will see that that will be a part that comes from the factors, a part that comes from the idiosyncratic component. And if you just redefine the loadings, in fact, it's basically this is if you want, is a factor augmented VAR, in the sense that this is a VAR forecast augmented with the forecast from the factors. Okay, this is just a selling point, because we will not use this formulation to make the forecast, but in fact, you can always rewrite everything you get in this way. Okay, it's just to tell you that this is what we're doing. And for those of you that know the paper by Stock and Watson on estimation with factor model, Stock and Watson are using just the first term, the one called factor here, to forecast your variable. So first they extract common factors from the predictor, and then they do direct projection of xt plus 1 onto the factors from t going backwards, and actually only on t, they don't have legs. So that's what they're going to do. Okay. Okay, so how does estimation work? This is for the practical user. Okay, we have a package on R for this. And then you first estimate the spectral density in the classical way. You need to select the bandwidth. I will say which one later on. You have to compute some autocovariances. That's the definition. And once you have the spectral density, sigma hat of x on a grid of frequencies, omega k, you just do principal component at each frequency. You pick the Q leading principal component, where Q is the number of factors that you should know in advance. And using only those, you will compute the common component spectral density, sigma chi, and then the spectral density of Xi is just obtained by difference. Okay, so that's a matrix which is not positive definite, it's positive semi-definite by construction, but it doesn't matter, because that's enough for our theory and an algorithm to go on. So cannot be inverted by itself. That's clear. Okay, so you see why we need to use a parametric model, because the long-run partial correlation network will be based on the inverse of this matrix at frequency 0, but I cannot take this estimated matrix and invert it, because that will not work, because it's semi-positive, it's positive semi-definite. Okay, it has rank p minus q, so it cannot be inverted. So in the second step, you have the VAR. Now I will assume VAR 1 for simplicity, otherwise notation is awful, and obviously we know that we can always use the companion form. So you get the autocovariances of the idiosyncratic component simply by inverse Fourier transform from the spectral density. And by using them, you can solve this minimization. So this is not Lasso, because Lasso will use Xi t. This is similar to Lasso, but if you want, this is a U-Walker. Okay, this is a U-Walker estimator. And obviously you have to pick a penalization constant lambda that I will discuss later on, but this is the problem that we minimize. Okay, and this is very convenient, because you just use second moment. You don't need an estimate of Xi t, and since Xi t is not observed, this allows you to control the errors much better, because you control that much better on the covariances than on the whole process Xi t, especially when you want uniform rates, because then you know, that would be very complicated. I mean, we have a result, but we show that the errors you get in this way are smaller. Okay, so third step, so this is enough if you just want the A's. Third step, if you want the network, well, then you have the formula. So what you need is an estimator of gamma, the covariance of the errors, and then the inverse. So first you get gamma, your worker again. Okay. And then delta, the inverse, can be obtained by this. This is a standard approach. Not saying that it's the best one, but this we borrowed from the literature, and we solve this problem. Okay, this problem doesn't give you a symmetric delta hat, but it can be symmetrized easily. And then in the end, your long-run covariance, spectral density at 0 frequency is given by this. Okay, so we will have results for all these terms. Now, what time is it? Okay. Some assumptions, try not to be too boring. So simply we need some conditions on the moving average filters The first one is for the common component, the filters loading the factors. This is just the square summability. It's nothing special. The only thing, this is the serial dependence, and we allow for serial dependence, which is not decaying geometrically. This is something we could have done with just, rho to the minus L would have been enough, but Heron was keen to keep this more general, so we have it like that. No, she's right. But this is nothing special, okay? What I want to comment is the second part. So these are the filters. These are the coefficients of the filter for the idiosyncratic component. Now, the idiosyncratic component is a P by P moving average, okay? The filter is P by P, and P is growing, okay? So the assumption here is that each of these entries is less or equal than a constant, which is specific to the entry, and then this part, okay? So this second term, again, controls the serial dependence in a classical way. So any weakly stationary process will satisfy it. Doesn't matter. This is not a big deal, obviously. So if you sum over L, this will converge, provided that this range sigma is greater than 2. Okay, so that's fine. But then you have the number of rows and the number of columns. Okay, and then this assumption is crucial, and this is basically what is implying that the spectral density has bounded eigenvalues. This controls the cross-sectional dependence. Okay. So the CIK is summable over rows and over columns. Okay, it might seem strange, but if you were able to order the cross-sectional units, the P cross-sectional units, then you could use the same kind of assumption you use in time series, and then this would be the case, because this would be stationarity cross-sectional, okay? So the problem is that you cannot order usually with a usual data set, there is not a preferred order of the cross-sectional units. So typically people make this kind of assumption, which are a little bit more abstract, but the implication is that one, okay? So because what does it mean, short memory in a cross-sectional context, okay? I mean, that's not something you can, I mean, there might be definitions, but then you enter a word that is something we don't want to do. So this is the way we make these assumptions. This assumption actually is borrowed from the work by Forni, Hall, and Lippi, and Zaffaroni, so it's not ours. Okay, just a notation. So I will use sigma and gamma without the hat for the true autocovariances and the true spectral density, and then the eigenvalues of a spectral density will be mu, and then this is for the common component, for the idiosyncratic component, for the data, depending on the index that you have. Given that, this is the crucial assumption, okay? The crucial assumption that we're making, which is what the data was showing us, is that the common component has spectral eigenvalues which diverge linearly in P, okay? And they are distinct. So the distinct eigenvalues is a technical assumption. But the important thing is that divergence in P, okay? So they diverge with P. This we've seen graphically that is likely to be the case. Here we assume that diverge linearly. That would be strong factors, as the literatures tend to call them. We have a result for weak factors. Honestly, I do believe they exist, as Alexei Onatsky was putting it 2 weeks ago, but I do believe they are not needed for this kind of studies. So I will not speak about them, okay? But we do have results. So if instead of P here, you put P with a different power, less than 1, some results are possible. Obviously, that power cannot be estimated in practice, so these are assumptions, but just to tell you that it is possible in principle, if you like that. And then the other one is the idiosyncratic component have the largest eigenvalue of the spectral density, which is uniformly bounded all over the frequencies, okay? And actually also from below, the smallest one is far away from 0, okay? Now, because of these two assumptions, there is clearly a gap between the two eigenvalues that increases as P increases, and this is what allows asymptotic identification of the model as P goes to infinity. Okay, so essentially the dominant cross covariances among the observables are those in the common component. This doesn't mean that the others are not important, but they have a different role, okay? So I wanted to spend 1 minute on an important result that tend to be forgotten when people speak about generalized dynamic factor model, which is the representation theory by Forni and Lippi 2001. This is a very complicated paper on econometric theory, which shows the following. It shows that if you do have a model, a data set, where you decompose into common idiosyncratic component with these two properties for the eigenvalues, which are the same that we assumed in the previous slide, then, and this is obvious, going down, also the data will have an eigengap. So the first Q eigenvalues diverge, the remaining one stay bounded. This is obvious going in this direction because it's Weyl inequality. It takes 1 second to prove it. However, the main important contribution of that paper is to show that the opposite is true as well. The vice versa is true as well. So if you find data that have spectral eigenvalues behaving like that, then there is a dynamic factor structure. Now, this is important because if you try to do the same with covariance matrix, that's not possible, okay? So when you have a covariance matrix, that's just a model. You can go that implication. So you will assume the first, and then you will say, then the data has this. Then you look on the data eigenvalues, and you say, well, if there is a factor model, this is the number of factors. This is the other way around. This is much more powerful because this is a representation result. This is an if and only if, okay? So that's what I was saying. If you look at the eigenvalues of spectral density, and you see that some are spiking, then there must be factor models according to this theorem. Obviously, there are assumptions that make this theorem work. So I'm not saying that this is always the case. Obviously, the spectral density must exist, first of all, okay? Because otherwise, obviously, you cannot prove anything. But it takes 10 pages to prove the other implication, okay? So I'm not going to give any other insight on it, but that's the result that I wanted to highlight. Okay, so now that I see this plot, given that theorem, I will say that the data is driven by common dynamic factors, okay? Because this is the implication upward that we had before. Okay, and then the last assumption is we have two innovation processes. One for the common component, UT, which is Q-dimensional. We assume that it's a martingale difference process, orthonormal, zero mean and unit covariance. We have to assume independence, but only cross-sectional between the units I and J, not in time, okay? In time is martingale difference. And the same for epsilon, okay? The same thing for epsilon, which is the idiosyncratic innovation process. We assume that common idiosyncratic innovations are orthogonal at every leading leg. This is what makes the two spectral densities, so one is the sum of the other two, okay? There are no cross spectral density between common and idiosyncratic, okay? This is standard as well. And then the last is that we just assume the existence of fourth moments, okay? We do not make other distributional assumptions. So nu will be the number of moments that we allow for. So 4 plus epsilon will work for our theory. Now, the way we derive the results, all our rates will depend on nu, so you can track this behavior in the rates. And when nu is equal to infinity, if in those rates you put nu equal to infinity, like a Gaussian, you will see what happens, okay? So the whole point is estimating the large spectral density matrix. And on that, there is a very nice literature by J.B.R. Wu that we used for our results. This is very technical, so I don't think I will spend much time. He introduced a functional dependence measure, which is defined here, which is, I find it particularly intuitive and interesting, but obviously people might prefer other measures. And if you can prove that your data has this quantity, what is this quantity? This is how much so you say your process is a measurable function of some filtration, okay, made of the two innovations. And then if you take that filtration and you change one innovation with an independent copy, you want to see how much your process changes roughly, okay, according to some metric, which is this norm written here, okay? If it doesn't change too much, then the functional dependence is bounded. Basically, there is dependence, but there is some weak dependence. And then you can do a lot of nice things, okay? So indeed, under our assumption, all this is satisfied by our data generating process. And it follows this fantastic concentration inequality that we have here, which is, you see that the two max are inside. This one is all over the frequencies, and this one is all over the entries of the spectral density matrix, okay? So this is as uniform as you can think of. And you have two pieces, the classical Gaussian tail here, And then you have something that depends on nu, depends on the tails, okay, on the extreme behavior. Obviously, there is the max, so that must enter somewhere. So then we play with this guy. Okay, then we play with this guy. So if our process satisfies this, our estimator of the spectral density satisfies this, and then we can work out what is the rate of convergence, which is here. Okay, so what we prove is that uniformly over all entries, that's the max norm, and overall frequency, that's the max here. The spectral density estimator of the common component obtained by dynamic principal components, so principal components on the spectral density of the data, converges to 0, to the true one, with this rate, which is made of 3 pieces, which are written, one is here, and the other 2 is 1 over m, 1 over root p. M is the bandwidth, and now we'll comment on this. And the same rate is propagated down for autocovariances, for spectral density of the idiosyncratic component, and autocovariances of the idiosyncratic component. Okay, so this is the rate that we're going to carry with us for the rest of the period. And now let's look at this rate. So it's made of 4 terms, okay? Now, the first term is the one that depends on the tails, okay? How big is nu? If nu goes to infinity, this is always negligible with respect to the others, okay? So for a Gaussian, you will not have this. But if you don't have a Gaussian, this you should acknowledge, okay? The second one, if there is not the log, you will recognize what you have when you estimate the spectral density. That's the variance term, okay? The log comes from the uniformity, because the max is inside the probability, but otherwise, root m over n is what you get when you estimate a spectral density matrix, okay? Is the variance term. 1 over m is the bias, okay? And 1 over root p is due to the fact that both the common component and the idiosyncratic component are unobserved, and so you need p to go to infinity to be able to separate the two. So that's the intuition of the rate, okay? And clearly, so if you are in the Gaussian case, or nu is large enough, in fact, you don't need Gaussianity, you need nu large enough to get rid of this first term, then you can balance these two terms and find the optimal m. And guess what? The optimal m is roughly n to the 1/3, which is the optimal non-parametric rate that you get when you use Bartlett kernel to estimate the spectral density. You change the kernel, this will change. And if you have a smoother kernel, this will go down faster, and then you will have a different rate, 2 over 5 you will get, okay? Which is the other typical case that you get. Okay, having said this, now let's see which kind of data can satisfy. So under which cases this goes to 0. Well, if p is of the order of n, then this will go to 0, okay? If log p is of order of log n, then you need a bit more moments to make this go to 0. If you are in a high dimensional case, ultra high dimensional case, so log p little of n, then you need sub-Gaussian tails to get convergence. But this is very large, okay? This means that p is almost the exp of n, okay? So this is ultra high dimensionality. But you can still get some consistency result. It would be nice to do these things with higher p and n. Honestly, we didn't have a large p for our data, unfortunately. Okay, so, well, then there is a lot of consistency about lasso. So let's keep that one, basically. Basically, this one is saying the same thing in a different way, that the autocovariances of the idiosyncratic component are estimated consistently. And then you have, okay, now let's use that Yule Walker approach penalized to estimate the coefficient of the VAR. This is the rate, this is the error bound that you get, which depends on what? On the penalty lambda, which in turn depends on two things: the rate of the estimation of the spectral density, previous step, and then this thing, the L1 norm of AXI. AXI is not symmetric, so the L1 norm controls the row sparsity because estimation is row by row. Okay, so that's what you care about. And then it depends on the square root of the in degree, which is the maximum number of non-zeros per row. Okay. If you look carefully, these are bounds, and you can well allow, at least when you have tails not too heavy, you can allow for the number of zeros in each row to still grow with p. Okay, because there are results where this number cannot grow with p. Then you know, then when p becomes very large, that's very, 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 very sparse. So okay, then it's easy to estimate it. You don't have many entries to estimate. So this is a point that we wanted to make. Okay, and then lambda depends on this thing. This thing, we didn't assume anything on this, but obviously we need to assume the sparsity to be something that is bounded, otherwise lambda will diverge, and if lambda diverges, there is no consistency. But we leave it like that, okay? We leave the rate like that, and then we reason saying, okay, this can be bounded. It's different from the number of non-zeros, okay? The L1 norm is smaller than this would be the L0 norm if you want, which is not a norm, but doesn't matter. Okay, so this is the first step. The second step becomes more complicated because obviously it depends on the first. Delta is the inverse of the covariance of the errors. And what it depends? It depends on the degree of penalization, which you have to tune based on the previous step. And it depends on the sparsity of delta. Here, row or column sparsity doesn't matter because delta is symmetric. So it's the same thing, okay? This can be the L1 or the L infinity norm, it will be the same. Okay? And then you put everything together and the omega matrix converges with this. I mean, as this bound, this is not convergence. This will be convergent if all this goes to 0. But in fact, if you look at lambda, if you pick lambda equal to this and A is bounded, lambda will go to 0. So this will go to 0. This, because of the way you choose eta, will go to 0. And this will go to 0 because lambda will go to 0 and eta will go to 0. Okay. Now here you have all the things that you had in the previous steps. So you have the rate of consistency of estimation of the spectral density. You have the row sparsity of A. You have the in degree. But now, since you're taking also the transposed of A when you do this omega matrix, is also the columns that matter. So you have the column sparsity of A that enters and the out degree, which is the maximum number of non-zeros per column. Okay, so all this quantity will matter in determining the convergence rate. Okay, all these three are bounds that do not guarantee sign consistency, okay? In fact, we know that if you estimate a VAR with lasso, you don't get VAR consistency, you don't get sign consistency unless you do, for example, adaptive lasso, because you need a condition that is typically not satisfied. So saying that the regressors with 0 coefficient and with no 0 coefficient should be uncorrelated. That's not the case in a time series. So typically you would need to do adaptive lasso. So adaptive lasso would be the way to ensure sign consistency, but that's annoying because you need a pre-estimator again. And so what do we do here? The other thing is, okay, you can threshold ex post. This can be shown to work. And obviously, however, you have to pick this threshold, which would be this T. So if you threshold using this T, then you will get the consistency of the sparsity pattern, and so also sign consistency, okay? And here as well, so basically you are saying that the true ones are staying really away from 0, so you can really discriminate between zeros and non-zeros, and at that point you also get the sign correctly, okay? And same, you can threshold this delta, and you can threshold the omega, okay? And the choice of these numbers is something we discuss empirically, and well, not empirically. There are ways, data-driven ways to do that. Okay. Okay. So now time. Ooh, I have plenty of time. Sorry. So this was estimation of networks. This is it. Okay. We said everything we could say, but we can also do forecasting. Now here I want first to make a disclaimer. Let's say. Intuitively, one might think that if you now try to forecast and instead of using only the factors, you use also the legs of the idiosyncratic component, you use more information, your forecast will improve. Now, for macro data, my experience says this is not going to work in the sense that there is no gain, okay? There is no gain in trying to forecast GDP beyond using principal components. Trying a lasso on the idiosyncratic of GDP, that's noise, because what is idiosyncratic in GDP in this large data set is basically measurement error. It doesn't really contain any useful information. So you might have gains numerically, but they are not statistically significant if you have them, okay? I mean, you might claim that if you try to forecast 200 series, then on average you do better, but which ones are you predicting better? Those that really matter, or maybe a random series which is completely idiosyncratic? Then obviously you're predicting it better because finally you're predicting it. Before you were not, because it was completely idiosyncratic. Okay, so my suggestion would be not used to this thing to forecast macro variables. And indeed we tried, and we gave up because there was no advantage. And here there were long discussion among us, okay? And then I said, you want to do forecasting, we do something on financial variables, maybe, where there is more idiosyncratic information, real information, okay, there. And so that's what we did. So there is a nice paper by Matteo Luciani in International Journal of Forecasting on 2014 showing this, that there is no value in trying to predict GDP using idiosyncratic models, okay? It tries Lasso, Ridge, a series of models that were proposed also by and Eng, but they also get the same conclusion more or less in a 2008 paper, I think, something like that, okay? So this is the point. So here, forecasting, we will apply forecasting to log volatilities of stock returns, okay? But before doing that, forecasting will be then a forecast of the common component plus a forecast of the idiosyncratic component. In order to study the bounds that you're gonna get for the forecast, you need bounds on the forecast of the common component. These do not exist for generalized dynamic factor models. So the result I'm going to show you now are new, okay? And again, they are uniform results. So even if you're going to use these models to forecast only the common component, these are the bounds that you're gonna get. Then we also had the lasso, because here we had the lasso part. But this is another contribution on the GDFM literature that didn't exist, okay? So there are two ways to forecast the common component. I mean, they are using the purely dynamic approach, okay? There are many other ways. If you use VAR for the factor state space approach, that's something we don't touch on here. Okay, so we have the common component spectral density, we have the autocovariances of the common component. So this 2005 paper is a JASA paper, which I think is beautiful because this is one of the it is one of the best ways to forecast. It works quite well, okay? So instead of applying principal component analysis on the covariance matrix of the data, apply principal component analysis on the covariance matrix of the common component that you get from the first step. Okay, and then this will be Stock and Watson. So project your data. So this is direct forecast. Project the T plus A observation on the T observation. And well, it seems magic, but you get this formula in the end. Okay, here there are some steps, but I don't want to spend time. Okay. If you were doing Stock and Watson, here you will have gamma hat of X. Here you will have the eigenvector of the covariance of X. Here the values of the covariance of X. Here the eigenvector of the covariance of X. And here you will have X. So replace chi with X everywhere. And this is Stock and Watson 2002, the way they forecast. Okay? And this is shown in their paper, in fact. So you can look at their paper to see why that is the case. But this is the kind of forecast that we consider and we call it static, because in order to be able to do that, you need to assume that the factors are loaded only with a finite number of legs. So that is what Lippi would call the restricted factor model, or Mark Callan would call it the restricted dynamic factor model, okay? Still, it's very useful, so I like it. Then they work on the unrestricted case, where they really allow B of L to have an infinite order. Then it's complicated because, first of all, they show that, in fact, the common component can be written in this strange way. So it has an autoregressive representation. But in general, A of L will not be a full matrix. It will be block diagonal. But then how do you select the block? I will not tell you anything. There is a way to do that. This is the reference paper, OK? But then you can estimate things again. So you start from your gamma chi of L that you get from the beginning. So same starting point. You estimate this polynomial by your Walker, again. And then you apply PCA on the filtered data, and you get R and U. This is static factor model. For the filtered data, they have a static factor model. So do PCA. Put everything together. This is an autoregressive model. You rewrite it as a moving average. So that will be an infinite moving average. You truncate at some leg K, and you get your estimated common component, which I call it VAR because it's based on a VAR representation. And then you can do recursive forecast because this is a moving average, and this will be the forecast that you get. Okay, so now we're going to compare what are the errors that you make using these two, and then I compare everything empirically. Okay, so for the first approach, the static approach, this is the error with respect to the unfeasible prediction. Okay, so this is just estimation error. This is not the prediction error, okay? Because this is the unfeasible prediction, which is this. And then the error has the nice property that we had before, okay? And then if you put A equal to 0, that's the in-sample estimation error. Okay. Now this is new because the 2005 paper doesn't have rates. They prove consistency without rates. So this, in fact, is telling you that the rate of consistency of the estimator that they had here is this one. Okay. So this is a contribution to that paper. On the other one, for the forecast, so this is the error due to estimation only, because this is the unfeasible prediction. It's more complicated because the unfeasible prediction will use infinite legs, while here you need to use a finite number of legs, so you need to truncate, so this capital K appears everywhere. So things might go wrong here in that case, okay? And then what we show is that, you know, if P and N are log P or log N are of the same order, then you can still get consistency things. You can find an optimal truncation leg such that then you get an error that goes to 0. The in-sample error rate is this one, which is the same that they had in this paper. So they had rates here for in-sample estimation. However, their rates were in L2 norm. This is a max norm, and that's why you get this log around here. Okay, but basically this is the same result that they had. Okay, so there are pros and cons. If I have to give a recommendation, I would use one for forecasting. I will use this for impulse response analysis because you see these are impulse responses basically. Okay, and then here you have a Q by Q matrix that you have to pick to do the rotation. But these are impulse responses. So this for impulse response analysis, it's very nice. This doesn't have a dynamic structure, so you cannot do impulse response analysis with this one. Okay. Obviously, if you want to forecast the idiosyncratic component, then you need to control the error on the idiosyncratic component, which is what we didn't want to control when we estimate the networks. But just to show you, that's why we didn't want, because that's the error you get. And you have this log P and this P to the 1 over nu that kicks in the rate when you put the max. And so this doesn't go to 0 in general. Okay, it's very difficult to do that. You first need light tails, you need the right lambda, but S in will go to infinity, then S in might not go to infinity. I mean, this can go to 0 under very specific circumstances, but it's less likely. And this is the reason why we don't want to do lasso on the Xi, okay? But we want to do lasso using the covariance matrices, because that error can be controlled much better. Okay, look, simulations are always simulations, so I will skip them. There is, I want just to say that we have a whole discussion on how to choose number of factors. This is standard stuff. How to choose the bandwidth. We said it's order n to the 1 over 3. We use cross-validation for this, cross-validation for this, cross-validation for D, and threshold for data-driven. There is a reference paper to how to show those thresholds. Okay, we have a whole paper, a companion paper of the R package where we discuss all these things. And in the R package, you can try all these things, okay? Good luck. I don't like them. But if you need to do things seriously, that's what you should do, okay? Some simulations go well. These are ROC curves for the estimation of the VAR1. So different configuration, everything works very well. Less nice when you estimate omega. Omega is a 3-step estimator, so there are some settings where this doesn't really work very well. Thresholding or not thresholding makes a difference between the dashed and non-dashed. So using that thresholding makes a difference, not a big one in some settings, in others. That's what it is, okay? Then we use log volatility, is the 46 that I showed you before at the beginning. And we estimate the 3 networks on a rolling window. This is 2006, basically. How do they look like? The non-zero entries are the one colored, okay? The rest is all 0. And then as the financial crisis kicks in, everything becomes more dense. Apparently here there is one company that is carrying all the load of the mess of the financial crisis, which I don't remember which one is. And after that, things change completely because from red you go to blue, from positive you go to negative links, okay? Whatever.
10 minutes, Matteo, as we said.
Yes, I'm done because this is the last slide.
No
so
worries. No, thank
we
you.
have plenty of time. So I can explain this slide with a little bit of calm, which is good. Okay. So how did we do forecast? So the forecast is done on a rolling window using only the trading days of 2012, and estimating with the data before. So these are 252 one-step ahead forecasts, okay? And then we computed two different error measures. This is the mean square error, okay? So this is the observed, this is the predicted, squared, the sum over all the series. So this is average over all the series, and then rescaled by the square of the observed value, okay? But since we have all these nice uniform rates, you want to see also the worst case scenario, so the max here, not the sum of the squares, okay? Because otherwise we did all those rates and then we look only at the L2, then what those rates are for, nothing, okay? So before explaining what the last column is, here I show you the forecast that you get when you use the static approach for the factors, okay? So the 2005 paper, okay? This is the mean square error, okay? So this is a given point in time. So this is the mean over the 252 points in time. This is the median over all the 252 points in time. This is our approach. This is a univariate AR. This is FunPredict. What is FunPredict? This is the paper by Fun and co-authors, where they do the following. First, they filter each series with a univariate AR model. Then they do Stock and Watson forecast, so similar to ours with factors, but using the covariances of the data and not of the common component. Then on what is left, they estimate a lasso on the idiosyncratic component in the standard way. They take the idiosyncratic component and estimate lasso, node-wise sparse bar. And then they put the three together and they have a forecast. Basically, they never do better than us, okay? And sometimes they don't even do better than the AR. In fact, what I suspect that this step is what they shouldn't have done, to be fair, okay? Because this step is already taking all the dynamics, or most of the dynamics with it. The rest is all static. This is completely static, and okay, this captures cross-sectional dependencies. This is something in between, but this is probably, once you've done this, this is almost useless. Whatever, okay? So this is what happens, okay? In their paper, they have an application of macro data, but I already said what I think about the applications of macro data. They show that they do better on average over all the McCracken and Eng data set, on average. But on single series, it's not clear what it is. I think it's very important what they do, though, because in their paper, they have something that we cannot do, which I think it's very beautiful. So I don't want to speak bad about it, because I like that paper. Okay, so let me give the last disclaimer just to be sure. Okay, in that paper, they show that with their results, they can test for covariant structures. If you think about it here, basically we are discussing on what is the covariant structure of the data. Is it sparse or is it dense? And they have a beautiful test on covariant structures, okay? They have a beautiful test. So I think, well, I mean, it's interesting for many things, but that is also a very nice thing that we cannot do. No way we can do that, okay? I don't think. They have nice other results that we cannot make, but it would be interesting to see whether the two things could be merged in that direction and have tests on the spectral density structure, for example. That would be interesting, okay? So now the paper is just published. Please do not download the JBS version, because I just discovered that the first version they uploaded, they removed all the hats on the estimated quantities. So you have A minus A, which is 0. But if you're interested in the paper, there is the archive version, which is typed in the right way. And then as I said, we have an R package and a paper on the R journal for technical details. Thank you very much.
Thank you very much.